Density functional theory, DFT, is a computational quantum mechanical modeling method used in physics, chemistry and materials science to investigate the electronic structure, or nuclear structure, principally the ground state, of many body systems, in particular atoms, molecules, and the condensed phases. Using this theory, the properties of a many-electron system can be determined by using functionals, i.e. functions of another function. In the case of DFT, these are functionals of the spatially dependent electron density. DFT is among the most popular and versatile methods available in condensed matter physics, computational physics, and computational chemistry. DFT has been very popular for calculations in solid-state physics since the 1970s. However, DFT was not considered accurate enough for calculations in quantum chemistry until the 1990s, when the approximations used in the theory were greatly refined to better model the exchange and correlation interactions. Computational costs are relatively low when compared to traditional methods, such as exchange-only Hartree-Fock theory and its descendants that include electron correlation. Since, DFT has become an important tool for methods of nuclear spectroscopy such as Mossbauer spectroscopy or perturbed angular correlation, in order to understand the origin of specific electric field gradients in crystals. Despite recent improvements, there are still difficulties in using density functional theory to properly describe intermolecular interactions, of critical importance to understanding chemical reactions, especially van der Waals forces, dispersion, charge transfer excitations, transition states, global potential energy surfaces, dopant interactions and some strongly correlated systems, and in calculations of the band gap and ferromagnetism in semiconductors. The incomplete treatment of dispersion can adversely affect the accuracy of DFT, at least when used alone and uncorrected, in the treatment of systems which are dominated by dispersion, for example interacting noble gas atoms, or where dispersion competes significantly with other effects, for example in biomolecules. The development of new DFT methods designed to overcome this problem, by alterations to the functional or by the inclusion of additive terms, is a current research topic. Classical density functional theory uses a similar formalism to calculate properties of non-uniform classical fluids. Despite the current popularity of these alterations or of the inclusion of additional terms, they are reported to stray away from the search for the exact functional. Further, DFT potentials obtained with adjustable parameters are no longer true DFT potentials, given that they are not functional derivatives of the exchange correlation energy with respect to the charge density. Consequently, it is not clear if the second theorem of DFT holds in such conditions. In the context of computational materials science, ab initio, from first principles, DFT calculations allow the prediction and calculation of material behavior on the basis of quantum mechanical considerations, without requiring higher-order parameters such as fundamental material properties. In contemporary DFT techniques, the electronic structure is evaluated using a potential acting on the system's electrons. This DFT potential is constructed as the sum of external potentials vexed, which is determined solely by the structure and the elemental composition of the system, and an effective potential VEF, which represents interelectronic interactions. Thus, a problem for a representative supercell of a material with n electrons can be studied as a set of n1 electron Schrödinger-like equations, which are also known as Kohn-Sham equations. Although density functional theory has its roots in the Thomas Fermi model for the electronic structure of materials, DFT was first put on a firm theoretical footing by Walter Kohn and Pierre Hohenberg in the framework of the two Hohenberg-Kohn theorems, HK. The original HK theorems held only for non-degenerate ground states in the absence of a magnetic field, although they have since been generalized to encompass these. The first HK theorem demonstrates that the ground state properties of a many-electron system are uniquely determined by an electron density that depends on only three spatial coordinates. It set down the groundwork for reducing the many-body problem of n electrons with 3n spatial coordinates to 3 spatial coordinates, through the use of functionals of the electron density. This theorem has since been extended to the time-dependent domain to develop time-dependent density functional theory, TDDFT, which can be used to describe excited states. The second HK theorem defines an energy functional for the system and proves that the ground state electron density minimizes this energy functional. In work that later won them the Nobel Prize in Chemistry, the HK theorem was further developed by Walter Kohn and Liu Sham to produce Kohn-Sham DFT, KSDFT. Within this framework, the intractable many-body problem of interacting electrons in a static external potential is reduced to a tractable problem of non-interacting electrons moving in an effective potential. The effective potential includes the external potential and the effects of the Coulomb interactions between the electrons, for example, the exchange and correlation interactions. Modeling the latter two interactions becomes the difficulty within KSDFT. The simplest approximation is the local density approximation, LDA, which is based upon exact exchange energy for a uniform electron gas, which can be obtained from the Thomas Fermi model, and from fits to the correlation energy for a uniform electron gas. Non-interacting systems are relatively easy to solve, as the wave function can be represented as a Slater determinant of orbitals. Further, the kinetic energy functional of such a system is known exactly. The exchange correlation part of the total energy functional remains unknown and must be approximated. Another approach, less popular than KSDFT but arguably more closely related to the spirit of the original HK theorems, is orbital free density functional theory, OFDFT, in which approximate functionals are also used for the kinetic energy of the non-interacting system.